So this is the first video for Chapter 8, which starts out reintroducing acids and bases. So this first video is just going to briefly go through the three main definitions of acids and bases. So really it's just defining them, giving you a couple examples, and then moving on. So Arrhenius acids and bases is the first category that we're going to discuss. So the Arrhenius acids and bases are specific to acids and bases in water. So you'll notice both the definition for the Arrhenius acid and the Arrhenius base only apply when the substance is dissolved in water. So the Arrhenius acid is a substance that, when dissolved in water, increases the concentration of H plus ions, which you may remember with water, H plus actually bonds with water to make hydronium, H3O plus. So the best definition, instead of calling it H plus, it's really H3O plus is the best. So an Arrhenius acid, it has to be dissolved in water, and by it being dissolved in water, it has to increase the amount of H plus ions. So think something that contains an H plus. So like HCl. Well, when HCl is added to water, it's a strong electrolyte, so it dissociates completely. And then HCl will break apart into H plus and Cl minus. So that would be something that increases the concentration of H plus in water. An Arrhenius base is something that, when dissolved in water, increases the concentration of hydroxide OH minus ions. So again, think of something that contains hydroxide and is an electrolyte, dissociates in water. So sodium hydroxide, lithium hydroxide, calcium hydroxide. So the strong electrolytes, things that are soluble in water, break apart 100% of the time, are the strongest acids and bases in this scenario. So everything that's an Arrhenius, based on the Arrhenius definition, is truly an acid or base. There's nothing wrong with this definition. The issue with the Arrhenius definition of acids and bases is that it is too narrow, because it only takes into consideration things dissolved in water, but there are acids and bases that exist that are true acids and bases that do not fit this definition, which is why there are multiple definitions of acids and bases. So the second one is the Bronsted-Lowry definition of acids and bases. So Bronsted-Lowry, that was actually two different scientists. They came up with this definition of acids and bases in the same year. So they were forced to share the fame. So they have to, both of their names are attached to this definition. This one is more general. It does not talk about just water. A Bronsted-Lowry acid is a substance that donates a proton to another substance. So it's a proton donor. Okay, so let me get my thing. So a proton donor just has to be something that contains a proton, which an H plus ion, if you think back to what you learned in Gen Chem 1, a hydrogen ion, it contains one proton, and if it's a positive charge, it has 0 electrons. So a proton is just an H plus. So a proton donor is something that gives away H pluses. This does not have to be dissolved in water. So that is not a rule we have to follow on this guy. So a Bronsted-Lowry acid donates an H plus. So a Bronsted-Lowry base accepts a proton. Again, a proton is an H plus because H plus is one proton, 0 electrons, bam. So a Bronsted-Lowry base accepts a proton. So a Bronsted-Lowry acid, we would recognize it if we're looking at a balanced chemical equation. The number of hydrogens that it has on the left-hand side, on the reactant side, is going to be greater than the number of hydrogens it has on the products side. So it loses an H+. Okay, a Bronsted-Lowry base is flipped. However many hydrogens it starts with, it has one more at the end than it did at the beginning. So this Bronsted-Lowry definition, we can determine what is an acid and what is a base by just tracking the hydrogens, counting how many hydrogens they have. An acid is something that has less at the end, and a base is something that has more hydrogens at the end. And that's the definition we're going to follow most of the time. In our situation, our acids and bases are going to be donating and accepting protons. Okay, so notice on that Bronsted-Lowry definition, it didn't mention water. This does not have to be dissolved in water. This could be dissolved in something else, or in the gas state, or in the solid state, or in whatever conditions you can think up. You see where it says sense BL, that's my way of being lazy and abbreviated Bronsted-Lowry, so that's what that is. So here's an example of an acid-base reaction based on the Bronsted-Lowry definition. So this one is done in the gas state. We don't see the states of matter listed, but I'm telling you, it's in the gas state. So HCl, notice that chlorine here starts out the reaction with one hydrogen And then if we find chlorine on the other side, it has 0 hydrogens attached to it. So 1 hydrogen, oops, 0 hydrogens. So in terms of protons, chlorine started with 1, ended with 0, so it donated. So this would be, based on the definition, the Bronsted-Lowry acid. Now if we look at nitrogen, nitrogen starts with 3 hydrogens. There we go, 3 hydrogens. If you look on the product side, it actually has 4. So it went from 3 hydrogens to 4 hydrogens, so it accepted. So that would make ammonia, NH3, a Bronsted-Lowry base because it accepted a proton. So when we're looking at acids and bases, if we're following the Bronsted-Lowry definition, the only difference between an acid and a base are the number of protons that it contains. An acid has an extra proton that it can then donate. A base has space to accept another proton. So when we're looking at an acid-base reaction, what is the acid on one side? So in this case, acetic acid, there in the blue. Once it donates its proton, what is left, the acetate ion, it then has space to accept a hydrogen. It's got an extra lone pair there. It's a -1 charge. It has a place to pick up an H+. So those are conjugate acids and bases. Acetic acid is the acid, and its conjugate base is the acetate ion. The only difference between them is the acid has 1 more proton than the base does. So if we look at the other 2 compounds in this reaction, methylamine, which is the Bronsted-Lowry base on the reactant side, becomes methylammonium ion because it accepts a proton. So now it goes from a neutral 0 charge to having a +1 charge. So methylamine is the base version, and its conjugate acid is the methylammonium ion. So again, the acid version always has 1 more proton than the base version. But when we're looking at an acid-base reaction, the reactants and the products are always the conjugate acid or base of the reactants. The last definition of acids and bases is the Lewis definition. So this is coming from the same scientist when you first drew Lewis structures with the lines and the dots and connected the atoms. That was the same guy. So the Lewis definition of acids and bases is about electrons instead of protons. So thinking back about what you know about protons and electrons. Protons are positively charged and electrons are negatively charged. So they're opposites in that way. So if the Bronsted-Lowry definition of an acid was something that donates a proton, if we want to look at it from the point of view of electrons, it's going to be the opposite. So if a proton and electron are opposites, something that donates a proton would then, the opposite of donate is accept. So Lewis acids accept electrons. Lewis bases, they donate electrons because Bronsted-Lowry definition, they accept protons. So protons and electrons are opposites. So in terms of accept and donate, they flip between the Bronsted-Lowry and the Lewis definition. So what this opens the door, the Lewis definition is the best technically definition of acids and bases because it covers everything. But what we see under the Lewis definition that we don't see under the Bronsted-Lowry are things that don't even involve hydrogen. Because if we're just looking at electrons being donated or accepted, that doesn't mean we have to have an H+. We just have to have spaces for 2 dots, a lone pair to go. So in this reaction that's shown here, the silver ion, the Ag+, notice it has no lone pair electrons around it. It's actually lost its 1 valence electron, that's why it's a positive charge. And then when you look at the cyanide ion, the Cn with a negative charge, you'll notice that both nitrogen has a lone pair and then the carbon has a lone pair. So those are electrons that it has in excess. So when they react, the silver goes from having no electrons around it at all to having 2 single bonds, 1 to each of the cyanides. So in that case, the silver ion went from having 0 electron pairs to having 2 electron pairs. So it accepted electrons. And then the carbon in the cyanide had 2 lone pairs kept to itself. Remember those individual dots? Those are lone pair electrons that are not in bonds, not being shared by anything, only on the carbon atom. To the products, carbon is now sharing those electrons with the silver. So it's donating the electrons. Now it's not giving them up completely, it's just sharing them. It's now no longer the only owner of those electrons. So if something fits the Lewis definition, that does not necessarily mean that it would fit the other two. Because if you look at this example, silver does not donate or accept a proton. It does not increase the amount of H pluses when it's dissolved in water. So the silver ion in this example, that was the Lewis acid, fits the definition only of Lewis, not of Bronsted-Lowry or Arrhenius. So same thing in this example for Lewis base. So the Lewis definition, it's the broadest. So if I took all the acids and bases that fit the Lewis definition, they'd live inside the circle. Okay. Then if I took all of the acids and bases that fit the Bronsted-Lowry definition and put them together, that's all of my Bronsted. So this is my Lewis acids and bases. That circle is my Bronsted-Lowry. All right, B, L. And then if I took all of the acids that fit the Arrhenius definition, this is a beautiful circle. All right, I'm going to draw this again, seriously. There's my Arrhenius. I'm going to draw a line. I'm going to write A for Arrhenius. There, that's where we go. So notice that the Arrhenius, everything that fits the Arrhenius definition, it is also inside of the Bronsted-Lowry circle. So if something meets the definition of an Arrhenius acid or base, it is automatically also meeting the definition of the Bronsted-Lowry. And if you look, the Bronsted-Lowry circle is also inside of the Lewis definition. So if something meets the definition of an Arrhenius acid and base, it also meets the Bronsted-Lowry acid and base definition and the Lewis acid and base definition. But notice that it's possible for me to find something that meets the Bronsted-Lowry definition that does not meet the Arrhenius definition. So it's possible for something to be Bronsted-Lowry but not Arrhenius. But if it is Bronsted-Lowry, notice all of the Bronsted-Lowry acids and bases meet the Lewis definition. So if it's Arrhenius, it's all three. If it's Bronsted-Lowry, it is Bronsted-Lowry and Lewis. The only way it can meet an acid or base can only meet one definition is if it meets just the Lewis definition. So this reaction on this slide is an example where silver ion is a Lewis acid, neither of the other two. Cyanide ion is a Lewis base, neither of the other two.